We've looked at factoring when we knew that the result was going to be two binomial factors, and when we knew the result was going to be a binomial factor squared. And we've looked at it when we know that the result is going to be the sum of two terms times the difference of two terms. What we haven't done is tried to do some factoring where we didn't know what kind of result to expect. So let's do a couple of those. Step 1 is always to look for a greatest common factor. There isn't one. There are no x's in this term, so x is not a greatest common factor because it's not common at all. The only number that goes into 15, 1, and 6 is 1. So there's no greatest common factor, but I did look, and that's important. If there is one, we need to factor it out to make the rest of our work easier. The second step is to find the product and sum. The product in this case is 15 times negative 6, which is negative 90. The sum is 1. Building negative 90, I can have a small negative number times a large positive number, or a small positive number times a large negative number. When I add these two together, I'm going to get a positive result. When I add these together, I get a negative result. I want my result to be positive, so I want my negative number to be the smaller of the two. So now I only need to look for combinations that when you multiply them together, give you 90, where the smaller number is negative. The next one in this list would be negative 10 times 9. But I already have 9 times 10, so I don't need 10 times 9. And besides that, the bigger number is negative. Adding these together would give me a negative result. So there's my complete list. Of all of these, the only one whose sum is 1 is this one down here. So these are the two numbers I need to use to break up my middle term. Rewriting my expression, but rewriting the middle term as minus 9x plus 10x. I get this. The greatest common factor of these two terms is 3x, and what's left over is 5x minus 3. Bring this sign down. The greatest common factor of these two terms is just 2, and what's left over is 5x minus 3. 5x minus 3 is common to both of these two big terms. So that's my greatest common factor at this stage. And what's left over is 3x plus 2. This is just like all the factoring problems we've done so far, except that I didn't necessarily know as I started what kind of result I was going to get. There are some that you can tell just by looking at what kind of result you're going to get, but that won't always be the case. If you're not sure, then just start factoring. Let's do another one. I'd like to do one that's actually very similar to this, at least at first glance. In fact, 15 times negative 6 is still my product. But this time my sum is 11. So I need to find a way to write negative 90 as a product of two numbers where when I add these two numbers together, I get 11. The problem is there isn't a way. I've made a complete list of all the ways to write negative 90 as a product of two numbers. And I've added them all together, and all of my results are positive, which I want, but none of my results is 11. All that tells me is that this polynomial cannot be factored, and that's my answer. We haven't run into one like that before. You start it the same way. Look for a greatest common factor. Find your product and your sum. Make a list of products. Find the sums of those products, and look for the number that matches this one. We've always found one before because I've always given you problems that will factor in order to show you how to do it. But not all trinomials factor. There's no 11 in this list. Yet this is a complete list of all the ways to write negative 90 as a product of two numbers. Okay, I've got negative 10 times 9 and negative 15 times 6 are not on my list, but that's just going to add up to negative 1, and this is just going to add up to negative 9. It's the same numbers as I've got in this list, but negative. 11 never appears in this list. So there's no way to split up the middle term so that I can factor it. It's not possible. So the polynomial cannot be factored. That's the first time we've seen one like that, but they do happen. This one looks a little different too. But the only tool we really have at this point is to just take our best shot at it. Our instructions here are to factor, and the first thing we always do is look for a greatest common factor. So what do x cubed and x squared both have in them? They both have a minimum of 2 copies of x. So the greatest common factor here is x squared. And what's left over? Well, what do I need to multiply by x squared to get x cubed? That would be x. And what do I need to multiply by x squared to get x squared? That's 1. This is it. That's as far as I can go. I can't factor it anymore. One factor is x squared. The other one is x minus 1. Here's a similar but very slightly different problem. Here's a similar but very slightly different problem. What do both of these terms have in common? X. What's left over? X squared minus 1. This looks just like the other one, except that one factor is only x and one factor is only x squared minus 1. But because this is a squared, it can be written as x squared plus 0x minus 1. In other words, there's a squared term but no x-only term, so I can put one in. Back here, there was no missing term. My powers, in this factor, my highest power was 1. So I've rewritten this one, and I can continue. My product is 1 times negative 1, and my sum is 0. How can you write negative 1? Negative 1 times 1, or 1 times negative 1? It doesn't really matter, does it? They both add up to 0. So I'm going to rewrite my middle term as negative 1x plus 1x. And then find the greatest common factor of these two terms and what's left over. Bring this sign down, find the greatest common factor of these two terms. They have nothing in common, but they do have 1 in common. And what's left over is x minus 1. The greatest common factor of these two terms, that's that x right there. The greatest common factor of these two terms is x minus 1, and what's left over is x plus 1. A very slight difference in these two questions resulted in really very different answers. Years of experience has taught me to look for things like this. This is the difference of two squares. But without that experience, the thing to look for is always the squared term. If you have x squared plus or minus anything, you may be able to factor it. Here I just had x. This is a linear factor. There's nothing else I can do with it. Let's take a look at another difference of squares problem. If you can see the shortcut here, recognize that this can be written as x squared minus 9 squared, then you can jump straight to x plus 9 times x minus 9. If you can't see that though, then try rewriting it. There's no x-only term, so introduce one. And carry on as before. My product is negative 81. My sum is 0. How can I write 81 as the product of two numbers so that those two numbers add up to 0. 9 times negative 9. So I'll rewrite my middle term as plus 9x minus 9x. Now I'll find the GCF of these two terms, which is x, and what's left over is x plus 9. Bring this sign down and find the GCF of these two terms, which is 9. What's left over is what I need to multiply by negative 9 to get negative 9x, and what I need to multiply by negative 9 to get negative 81. The greatest common factor of these two terms is x plus 9, and what's left over is x minus 9. So a problem like this can be factored even if you don't know the shortcut, and in fact, even if you don't recognize it as the kind of problem that has a shortcut. You can still factor it. You just have to notice that because it has a squared term in it, it's possible that it can be factored. Because it does not have an x-only term in it, we need to introduce one. Beyond that, this is the only difference between this and any other type of problem. I'd like to do another one, again, very similar to this. I'm going to try and fit most of it on the same screen. How do you factor x squared plus 81? Well, again, there's no middle term here, so I'm going to introduce one. And carry on as normal. My product is 81. My sum is 0. Everything's positive, so I don't need to worry about signs down here. It's always going to be a positive times a positive. What are the different ways that I can write positive 81 as a product of two numbers? That's it. The next one on the list would be 27 times 3, and I already have that here. When I add these together, I get 82, 30, and 18. None of these is 0, so this cannot be factored. If you know the shortcut, you'll know that the difference between this problem and this problem is the sign between the two terms. It turned out that the first one, the x squared minus 81, can be factored, but the second one, x squared plus 81, cannot be factored. Again, memorizing shortcuts is only as good as your understanding of the concepts to begin with. If you picked this up, or if you recognize it, or if you've already done this in another class, and you can use the shortcut to say that this cannot be factored, then that's fine. But if you're not sure, just try it. When something can't be factored, it'll show up in this step right here. None of these numbers matches the sum that we need. There's no way to build the product of two linear factors in such a way that it'll give us x squared plus 81. Let's do another one with just two terms. This one looks a little daunting, but once we've factored out the greatest common factor, I think you'll find it's not quite as difficult as it looks. What do negative 4 and negative 100 have in common? What goes into both of them? Negative 4. And in fact, even if this had been a plus sign, I would have factored out a negative 4, because that means what's left over is easier to work with. I have 7 copies of x here, but only 5 here. If I undistribute 5 copies, I'll be left with 2 copies here, because negative 4x to the 5th times x squared is negative 4x to the 7th. Now, I've undistributed a negative, so I'm looking for what do I need to multiply negative 4 by to get negative 100? A negative times a positive is a negative, and 4 times 25 is 100. And x to the 5th times 1 is x to the 5th. So I could write times 1 here, but I don't need to. Okay, now I have an x squared term here. So, although I factored out my greatest common factor, I might be able to factor this further. In order to find out, though, I need to rewrite this with a middle term, an x-only term. Then I can continue. But notice that I'm writing down my big greatest common factor, the one I pulled out from this step. I'm writing that down in each line here. Okay, let's figure out how to rewrite 0x. My product is 1 times 25. And my sum is 0. So how can I write 25, everything's positive, so that the sum of its factors add up to 0? I can't. So this doesn't factor. Does that mean I scratch the whole thing out and say this doesn't factor? No, not at all. Look, I did factor it. This is the factored form of this. It's just that this factor doesn't factor anymore. So this is actually my answer. If instead I had asked you to factor this, which looks very similar, I would have started the same way. Factor out a negative 4x to the 5th. What's left over is 1x squared minus, this time, minus 25. Negative 4x to the 5th times x squared is negative 4x to the 7th. And negative 4x to the 5th times negative 25 is positive 100x to the 5th. Recognize there's a middle term missing here, and rewrite this expression with an introduced 0 term. Now we have a product of negative 25 and a sum of 0. And I can write negative 25 as negative 1 times 25, 1 times negative 25, 5 times negative 5, or negative 5 times 5, which is the same thing as I have here. The sum of these two numbers is 24, the sum of these two numbers is negative 24, and the sum of these numbers is 0. So in this case, I do have a way to write my 0 term so that the numbers add up to 0 but multiply to negative 25. So I'll rewrite the problem again. With my middle term split up, plus 5x, minus 5x. Rewriting my first greatest common factor, I'm now going to look for what's common to these two terms, which is x. And what's left over is x plus 5. Bring this sign down. What's common to these two terms is 5. And what's left over is x plus 5, because a negative times a positive is a negative. What's common to these two terms is x plus 5. And what's left over is x minus 5. Again, at this point, you might have said, oh, look, that's a difference of squares. And if you saw that, you could have jumped straight to this line here. But if not, I hope you'll recognize that this process is the same as for any other problem. This is my final answer in this case, whereas this is my final answer in this case. And the only difference between the two of them is that this one had a minus in this position and this one had a plus. Also recognize, though, that this one is not a cannot be factored problem. We just couldn't factor it very much. We found a greatest common factor, and that's a factor. And the other factor, well, that's all we could do with it. Problems like this one require a little bit more finesse. The first thing I have to do here is to be able to recognize that t to the 4th can be written as t squared squared. And my 1 can be written as 1 squared. So if there ever was a case for needing a shortcut, it might be arguable that this was the case. The difference between two squares will always factor like this. And it doesn't matter what a and b are. For example, I might have x squared minus 16, and that would factor as x plus 4 times x minus 4, because 16 is 4 squared. 4 is my b. Or I might have 81 x squared minus 100, and that can be written as 9x squared minus 10 squared. So that factors as 9x plus 10 times 9x minus 10. 9x is my a squared, and 10 is my b. So here, my a, the first thing squared, is t squared. So I'm going to get t squared plus and t squared minus. My a is t squared. My b is just 1. So this is factored, but it's not finished, because actually t squared minus 1 is another difference of squares. So I can write t squared plus 1 times t squared minus 1 as t squared plus 1 times t plus 1 times t minus 1. T squared plus 1 does not further factor. For the rest of this quarter, a question like this would be a bonus question, because I've already told you I don't care if you memorize a shortcut. But you will see a problem like this again, if not in Math 98, then certainly later on in your career. Almost all of you will have to get through Math 141. And I'd be very surprised if you didn't see a problem like this at some point between now and then. So I'm not going to ask you a problem like this unless I give it to you on an exam as a bonus question. But it's certainly worth having addressed, as you're quite likely to see it in the future.